Hello, my name is Héctor Gil-Marín. I'm coming from the University of Barcelona, and today I'm going to talk about the large-scale galaxy surveys as a cosmic lab. So in my talk, I'm just going to give a brief introduction on who I am and what's my career. Then I will talk about the background in the large-scale structure of the universe, and then I will continue with my research and my future plans of research. So I did my PhD at the University of Barcelona, mainly working with synthetic data, developing tools to better extract information from the large-scale structure of the universe. In 2012, I moved to Portsmouth to start working with the BOSS survey and to start working with real data and get cosmological constraints out of this. In 2015, I moved to Paris with a Lagrange fellow, and I started to get involved in survey EBOS, which was the natural continuation of BOSS. And finally, in 2018, I moved to Barcelona, back to Barcelona with a junior leader La Caixa fellowship to work on DESI. So within these years, I've taken several positions of leadership within EBOS, within BOSS. I did the official analysis on the BEO and RSD power spectrum, as well as the first measurement of the bispectrum signal in BOSS galaxies. Within EBOS, I was chair of the Quasar and Galaxy Working Group, and I did as well the first BEO and RSD measurement of quasars at high redshift, and as well contributed or lead the final analysis on the BEO and RSD of the high redshift luminous galaxies. Now within DESI, I'm a convener of the key project that will measure the RSD and FNL in DESI year one data in 2022. And I'm also one of the authors of the blinding proposal within DESI to avoid confirmation bias. During these years, I have supervised two PhD students, Rosanna Ruggeri in Portsmouth, and right now Samuel Briden in Barcelona, both working with the connection between how to extract cosmological information from real surveys. And I'm also right now advising a master's student at the University of Barcelona working in high order statistics. So I'm going to start reviewing what's the main problems in cosmology today. So we have this so-called lambda CDM model, which is a model that is phenomenological and it describes very well the observations, but we have two main problems. One of them is that we don't really understand what's this dark energy or lambda that is driving this accelerated expansion in the light universe. And the other problem is that we don't really understand what happened at inflation time. We don't understand what was the conditions of physics on the Big Bang. We don't understand the singularity. We don't really know anything about inflation and any kind of new physics that is there. So in order to get information on these mysteries, we have observations, and right now we only have electromagnetic observations in the spectrum. So apart from the nearby observations on supernovae, we have two sources of information. One is the CMB, or the early time physics, and the other is the early time physics, and the other is the galaxies, or the late time physics. So we have already observed a lot of temperature modes in the CMB, which has confirmed this model, lambda CDM, but we just started to extract information from these galaxy surveys of the late time universe. So the information in the galaxy surveys is much more interesting than in the CMB, first of all, because it happens at the same time as the dark energy start acting. And it also contains many more, because one is a 2D, it's a sphere, the CMB is a sphere, and the late universe, the galaxies, is just a 3D. So it's not just the surface of the sphere, but it's everything. However, there are several things we have to take into account in order to extract information from the galaxy surveys. One is the nonlinear gravity evolution that in principle is complicated to model. and the other are like peculiarities in the observations, like the peculiar velocities, or the fact that the physics that we don't observe dark matter, we observe galaxies, and the physics that drives the formation of galaxies on the top of dark matter are complicated, and we need to understand. So we have these galaxy maps that we have observed so far, and the current state of the art of these maps are the ones provided by Bose and Ebos, at least in the spectroscopic side. And these are like the state of the art of the maps, which are mainly covering the redshift from now up to redshift 0.3. And then this map represent, each point of this map represent an spectroscopic observation of different samples of galaxies, from Lyman alpha at high redshift to bright galaxies going through quasars, ELGs, and LRGs. And from each of these samples, we can extract cosmological information and then say something about the universe. So the position of the galaxies are intrinsically stochastic, which means that if we want to characterize the map, we need to do it through statistical functions. And these are like correlation functions. So the simplest correlation function is the 2-point correlation function, or the power spectrum, and which contains the Gaussian part of the signal. And on the other hand, we have higher order statistics, and the simplest higher order statistics is the bispectrum, or the 3-point correlation function, which is like the first non-Gaussian part of the signal. So in the early universe, a bispectrum equals 0 implies that the FNL and GNL, or the primordial non-Gaussianities, are 0, which means that a Gaussian field is essentially characterized only by the power spectrum. But in the late-time physics, in the galaxies, the bispectrum has two contributions apart. One is the primordial, but we have another which is way, way stronger, which is the gravitational part. So in the late-time universe, the bispectrum of galaxies is going to be non-zero because of the gravity evolution. And because of this, the direct measurement of the primordial contribution of this bispectrum in the galaxies is not easy to observe. In order to give a more visual interpretation on what the power spectrum and bispectrum are, we can think of power spectrum as a way of counting pairs separated by a certain scale, which in this plot is represented by the size of the stick. So if we count how many pairs of separated by this size of the stick are on our distribution, on our observed galaxy survey, and we compare it with the pairs that we would expect with a survey without any clustering, we have what it's called the 2-point correlation function of the excess of clustering of our survey. And of course, this is related to the probability of finding two galaxies separated by this distance given by the size of the stick, given a density of our survey. So we can extend this visual interpretation to the bispectrum, and then substituting simply the size of the stick by a triangle, which will have a size as well, but it will also have a shape. So in order to characterize the discounting, then we will have to take into account not only how this probability of finding now 3 galaxies depends on the scale of the triangle, but also with the shape. So as before, the counting of triplets with respect to a random distribution is what is called the full 3-point correlation function. In reality, this 3-point correlation function depends on the excess of the pairs for each size of the triangle, which are represented here, but it will also have an extra contribution, which is called the connected 3-point correlation function, which is what we usually refer as the 3-point function or the bispectrum. So the characterization of the map comes from actually extracting the 2-point statistics, 3-point statistics, 4-point statistics, and so on. So the more statistics we have, then the better we have this map characterized, and therefore the more information we can extract. So for Gaussian fields, the bispectrum is 0, as we have said before, and the trispectrum is not 0, but is a functional part of the power spectrum. So if our field were Gaussian, then only by measuring the 2-point statistics of the power spectrum, we could fully characterize it. But it happens that in the galaxies, in the late-time universe, the field is fully non-Gaussian, and therefore we are going to need to measure more statistics beyond the power spectrum. So coming back to cosmology, there are mainly two physical effects in the universe that allow us to extract cosmological information. One is the Baryon acoustic oscillations, and the other are the redshift space distortions. I'm just going to review them briefly. So the BEO, the Baryon acoustic oscillations, is something we use in the universe to calibrate our distance measurements. So the origin of these oscillations happen in the early universe. We have a plasma that contains baryons and photons, and these two elements are coupled. They oscillate and they generate pressure waves that travel through the plasma. So at some point, the temperature drops below a certain threshold, and there is this decoupling between photons and baryons, and then the plasma disappears, and this wave pressure, the waves frozen at a certain distance. So this distance is called the sound horizon at drag epoch. And this serves us as a specific measurement that we can detect. So we can detect it on the top of the CMB surface, but we also can detect it in the galaxies, because this pressure, this excess of pressure in the wave gets captured later by dark matter when dark matter traps baryons, and also by galaxies, because galaxies lives in the or born in the peaks of dark matter. So this sound horizon scale is of order of 150 megaparsecs, and this special distance is something we can measure when we measure the 2-point correlation functions of temperatures in the CMB, but also when we measure the 2-point correlation function of galaxies. So if we work in comoving distances, the size of this BEO doesn't change, and therefore we can calibrate our measurements by knowing that the size of what we are measuring has to be 150 megaparsecs. Obviously, in physical distances, this distance changes as the universe expands, but this also helps us to calibrate the expansion of the universe, because we know that if the expansion is given by a certain cosmological model, this sound horizon has to change accordingly. So in order to do this, we do what is called the Alko-Paczynski effect, and this is by assuming that the cosmological principle, so that the universe is homogeneous and isotrope. So this means that by the homogeneity, the BEO has to be a spherical structure, which means that when we measure the BEO signal along and across the line of sight, this has to be the same. However, what we observe are not distances, are redshifts, and in order to convert redshifts to distances, we need to assume a cosmological model. So if the assumption of this cosmological model is wrong, this is going to generate an anisotropy, because we are going to distort the clustering along the line of sight, which are like these redshifts, with respect to the clustering across the line of sight, which are not affected in the same way by this transformation of redshift to distances. So by comparing the BEO along and across the line of sight, we can say whether our conversion of between redshift and distances is correct or not, and this is what is called the Alko-Paczynski effect. So the BEO, or the distances, but in particular the BEO distance along the line of sight, is characterized by this DH, or 1 over the Hubble factor, whereas across the line of sight is dm, which is the integral of the Hubble factor between 0 and the observation point, which is called the angular diameter distance. So more specifically, we can say that our wave vectors are distorted the true wave vectors are connected to the observed wave vectors by this distortion parameter, which is Q. And this Q is mainly going to be the ratio between this DH or DM of the true universe with respect to the fiducial model that we have used to convert redshift into distances. So if by chance we happen that our fiducial model is the correct model, then Qs are 1, and therefore our observed wave vectors are the same as the true vectors. But if not, then these Qs are going to be different than 1, and visually the effects, they are going to have two effects. So one effect is the Alko-Paczynski, that they are going to generate an anisotropy signal, and they are going to distort the BEO along and across the line of sight different. So in terms of the power spectrum, this has two effects. One effect is to generate an anisotropy, as we have said before, and another is that they are going to move the spectra on the wavelength direction, because the wavelength gets distorted by these factors. And visually, this is what happens with the BEO distance. So this Alko-Paczynski effect actually constrains the ratio between these two BEO distances, the DM over DH. And on the other hand, we have the isotropic shift of the BEO, which it doesn't generate any isotropy, but it changes the position of the BEO. And this is just moving right and left the power spectrum. So this is characterized as dV. So these two wave vectors can actually be written as two distortions in the BEO. One is the isotropic distortion, and the other is the anisotropic distortion, which is what is known as Alko-Paczynski. There is an extra complication to this model, is that this effect only comes from converting redshift into distances. So if we know which is the true position or the true value of the BEO at CMB times, that's fine. We don't need any more information. But in general, because we don't know the contents of the universe, we don't know the amount of baryons, we don't know the amount of matter, we don't neither know which is the correct value of this sun horizon at drag epoch. So we need actually to marginalize over that. So this only enters, this enters actually as an extra factor of these Qs, which multiplies by this ratio, and they form these so-called alpha parameters that they are going to be our natural parameters in our model. So our wave vectors are not going to be distorted only by Alko-Paczynski, but now they are going to contain as well this extra unknown on what's the actual position of the BEO. However, notice that when performing the Alko-Paczynski test, which is just measuring or looking at what's the relative change on the BEO along and across the line of sight, this does not have any effect because the absolute value of the BEO cancels out. So in terms of Alko-Paczynski, this doesn't really add any extra complication because the actual value of the BEO distance, it doesn't matter. However, for the isotropic shift, it does matter because it can be that we observe that the BEO, it's farther away from what we expect it to be by either having a drag epoch, which is smaller, or because having a wrong cosmology, which induces that the BEO shifts towards that position. Another effect are the redshift space distortion, and this comes from the peculiar velocity. So we transform redshift into distances, assuming that the movement of galaxies are according to the Hubble flow. But we know that the galaxies have peculiar velocities, which are induced by the nearby galaxies, and therefore by the amount of matter in the universe, as well as by the law of gravity, because these two galaxies interact according to the theory of gravity. So along the line of sight in the radial direction, we will have a contamination coming from these peculiar velocities that we will induce an extra source of an anisotropy, which will increase the clustering along the line of sight with respect to the clustering across the line of sight, which is not affected because we don't detect peculiar velocities across the line of sight. So again, this generates a source of anisotropy, which in this case is coherent with the growth of a structure F. And by measuring this amount of anisotropy, we can say something about depth. So we have these two effects. Alko-Paczynski, which generates anisotropy and shift BO peak positions, and redshift space distortion, which also generates anisotropy, but does not change the BO peak positions. And this is key in order to disentangle these two effects. So this is essentially what we have said. The anisotropic part can be generated either by Alko-Paczynski or RSD, and the RSD induces an amount of clustering, but AP in principle does not. So knowing that how the spectra, the power spectra, can be moved up and down or left and right with these different processes, then we can break the degeneracy and measure what usually are our free parameters of our model, which will be this F sigma 8 or extra excess of clustering due to redshift space distortion, and BO peak positions that will depend on Alko-Paczynski parameters and also the absolute position of the BO. So this is what we do usually in spectroscopic survey, and this is what is called the full shape analysis. There is another kind of analysis which only focused on the BO peak positions, ignoring this, and this is called BO type of analysis. And from both of them, we can extract cosmological information in these three sets of parameters. And here I'm just showing a picture on how this is done using, in green, a full shape analysis of the monopole and quadrupole, which is the first anisotropic signal, and also including the hexadecapole in red. So adding the hexadecapole is just adding a bit more information in terms of anisotropic content, which allow us to break more efficiently the degeneracy between the anisotropic part induced by BO or Alko-Paczynski. So right now I'm just going to present briefly, very briefly, some of my research lines. So these can be essentially divided in two parts. One is those research that they are focused on connecting a theory model with an ideal realization of the universe. And the other is the implementation of statistical techniques in actual surveys to get cosmological information. So I'm going to start by this paper here called Blind Observers of the Sky that I did along with my PhD student. And this paper aims to present a way of blinding galaxy survey catalogs in order to avoid confirmation bias. So this is modifying our observables in our galaxy catalogs in order to avoid knowing the true answer when we are performing the analysis. And why we want to do this? We want to do this because we want to avoid this effect called confirmation bias, that is that even if each new measurements it's done in principle out of any prejudice, it's always influenced by what people have done before, and therefore we are afraid of finding something which is out of normal. So we are unconsciously going to start looking for effects that drives our measurements out of what happened previously before. And this is bad because this stops us of discovering new physics or new physics. So this is like exemplified here as the neutron lifetime as a function of the year of the experiment, where you see that within a period of time until the error bars really cannot shrink very much, most of the measurements go on the same value, and then there is a jump, and then we go in the same value, and there's a jump, etc. So we want to avoid this because this is like each measurement here is like really affected by what people did before. And same thing happened with the Hubble constant. So we want to do this. I mean, there are like different ways of doing this, but we want to do it at the most basic level, which is modifying the positions of our galaxies in our catalog in order to do so. So we want to take our original catalog and then apply some modifications that imprint some fake signal in such a way that when we analyze this blinded catalog, we don't know which is the signal we expect. And for instance, we can induce some non-lambda CDM or some weird lambda CDM signal. So when one goes and measures this alpha parallel, alpha perpendicular F sigma 8 on this catalog, he knows that he doesn't have to get a lambda CDM consistent result because this catalog has blinded. So he can perform all the systematic tests, he can play around with the catalog without really having this prejudice in finding lambda CDM. So this has some pros, which is that you consistently blind all the statistics at once because you modify the catalog, so you can perform consistently analysis on the power spectrum in Fourier space, in configuration space, or the higher order statistics, or analysis on voids, because all of them are going to be consistent within this blinding scheme. The cons are that this is a complex process, that just blinding the summary statistics that would be much easier. So how we do this blinding? So actually we do it by two steps. The first step is modifying the angular. So we don't want to touch the angular positions because these are not actually blind in galaxies, in redshift galaxy surveys. The imaging of these surveys is not blind. And the only thing we want to blind is the radial distance, the redshifts, which is the actual added value of these catalogs. So first of all, we are going to do in two steps. First of all is a geometrical shift, like an Alkop-Paczynski shift, and the other is a density-dependent shift. So this first shift is going to modify the BEO, the true BEO position of the galaxies along the line of sight, and this second shift is going to modify the growth of the structure. So the first blinding, the DEO blinding, it consists of you start always by choosing an arbitrary cosmology, which is your fiducial cosmology, and then you start by transforming the redshift of your catalog into distances. But then you choose like a shift cosmology, which is like, can be your fiducial cosmology with some extra thing that you in principle don't know, you are blind to this chosen cosmology. And then you retransform distances back into redshift, but using this shifted cosmology. So now you have blinded redshift, and then when this is what it conforms your blinded catalog, and then when you give this to the people who are doing the analysis, then these people are going to take these redshifts and transform it into distances, but now they are going to have blinded distances because they don't know which is this shifted value. So actually the alphas that you observe using the fiducial cosmology are the true alphas that you would expect to get from the unblinded catalog. And then the alphas you get from analyzing your redshift under the same cosmology are called the blinded alphas. So actually the true alphas with respect to the blinded alphas can be connected a posteriori without having to rerun your analysis, just by knowing which is your shift cosmology and knowing which is the fiducial cosmology you have used. The second shift is a bit more complex, but it also induces a modification on the growth of a structure. And the trick here is using reconstruction. So reconstruction essentially tries to, looking at the position of the galaxies, knowing which is the bias and the growth of a structure that the galaxies may have, then you infer which is the position of dark matter. And knowing the position of dark matter, you can also trace back how these galaxies would have evolved under different conditions. So the idea is to subtract the signal from redshift space distortions and add a fake signal of redshift space distortion, in that sense that you are going to modify the positions of the galaxies in a clustering dependent way, and therefore you are going to induce a growth of a structure which is different from the growth of a structure that these catalog have. So when you measure the growth of a structure and BEO on this blinded catalog, you're going to have different things than what is in the unblinded catalog. And this is exemplified in this way. Then we take the CMAS BOS data, and here in blue, they represent the BEO signal on the original catalog. And in red, the signal that you get when you measure these BO wiggles in the blinded catalog, what we have applied at this two-step process blinding. So already by eye, you see that the measurements shift and also the best fit model shift. And this is how the different parameters you get from the catalog. So in blue, you get the contours on alpha parallel, alpha perpendicular, and F sigma 8 on the original catalog. In red, you get the contours from the blinded catalog. So you see that there is a shift. And actually, you can shift back the blinded results into the original results just by knowing which is the shifted cosmology that have used to produce this blinded catalog. So actually, without having to redo your analysis, just by applying this shift that is represented in this way by this arrow, you can see how well you can recover the original signal without having to rerun anything, not only on BEO quantities, but also on F sigma 8. So more into how we extract cosmological parameters from galaxy surveys. I have worked both in BOS and eBOS tracers. So among all these two galaxy surveys, we have covered a huge redshift range on clustering that goes essentially from redshift 0 up to redshift 3.5. And what we have done is to measure the 2-point and 3-point, in some cases, statistics from each of these galaxy samples and extract alpha parallel, alpha perpendicular, and F sigma 8. So this is the different spectra, power spectrum monopole, quadrupole, and hexadecapole from different galaxy samples. In that case, for the eBOS one, the LRGs at redshift 0.7, the ELGs at redshift 0.85, and the quasars at redshift 1.5. And from each of these measurements, we compressed all this information in just 3 cosmological parameters, which are alpha perpendicular, alpha parallel, and F sigma 8. And once we interpret these 3 parameters within a cosmological model, then we can drive some cosmological inference. So just to exemplify it here in this way, this is the angular diameter distance along the line of sight. This is essentially the Hubble parameter, which is the BO across the line of sight, and this is F sigma 8. In green is just the prediction by lambda CDM with Planck measurements. And these different dots shows the measurements from the different samples of BOS and eBOS. So just to exemplify how good the BO detection is in terms of precision, I'm just showing the BO across the line of sight for the main galaxy survey, which is redshift very low, and the different LRG samples, ELGs and QSOs, and you see that the BO precision is around 1 to 2% in most of the cases. So we can say few things about the universe with these BOS constraints. So we now have 3 independent proofs of dark energy, or lambda. One is the CMB alone, while the other are the supernovae. But now we have as well SDSS measurements or BEO measurements that just alone, they can rule out dark energy equals 0. So when the unfair advantage of BEO with respect to the other ones is that actually we have observations at different distances. So this is very efficient on breaking degeneracies and allowing to get constraints on good constraints on omega lambda. So also because of this, BEO allow us to tell us information about the flatness, and actually when BEO is combined with CMB, which CMB means either Planck or other observations like WMAP, we can mainly say that the universe is very consistent with flat one, that in this plot is represented by this dashed line. Another interesting thing is what has this galaxy BO to say about the Hubble tension. And as I've said before, the BO has this degeneracy between the actual position of the BO that we observe on the galaxies and the position of the BO on the CMB. So the position of the BO on the CMB is this sound horizon scale, but in our analysis, we are measuring alphas, which are essentially these Qs, which is DH over DH fiducial times RS over RS fiducial. So when we obtain a measurement of alpha, it can either be produced by like a pair of measurement of H naught and RS, which are actually degenerated across this line. So our measurements of BO alone can either indicate that we have like a huge measurement of H naught, which corresponds to a low measurement of the sound horizon scale, or the other way around, that we have a low measurement of H naught that corresponds to a high measurement of RD. So this is represented by this line here. And then when we combined our measurements with extra data sets, then we can say something about H naught. So the distance ladder measurement produced an H naught, which is around 74, and Planck alone, which is here, produces an H naught value, which is consistent with 68 or 67. So we can combine either BO with BBM, which is in principle not directly combining BO with Planck, and then we get a consistent result with Planck in terms of H naught and RD, which is represented by this dark blue line. We also can combine our BO measurements with the RD, or we can combine our BO measurements with the H naught that is measurement from the distance ladder calibrated with the supernovas, and then our measurements are consistent as well with them. But in that case, we get a high H naught value at the expenses of having a really, really high tension on RD with the measurement of Planck. So either you can see this as a tension in terms of H naught, or see it as a tension of on RD. So in case of we combine CMB Planck with BO and with uncalibrated supernovas, allowing full freedom in terms of our cosmological model, in terms of open universe and dynamical dark energy parameterized by W0, WA, then we get this pink line here that is again consistent with Planck. So unless we force the RD to be really low, there is no way that we can fit BO consistent with the distance ladder. We're always going to have like a low measurement of H naught. A bit off topic to this is like all these cosmological measurements have been inferred from actually measuring the 2-point statistics, but there is actually a lot of information, as I've said before, in the 3-point statistics. And this was shown in this paper where we measured actually the bispectrum of BOSS, the 3-point statistic signal, and the first, which is represented here. So here I'm just showing the 2-point statistics for comparison. And in this plot here, the top plot is showing the detection of the bispectrum. So the first thing you see that the bispectrum is really, really detected, is really different than 0, which give us an idea of how non-Gaussian the actual signal is. And in black, I'm just plotting the best fit model. So you can think of how much information this bispectrum adds. So it actually adds information in 2 ways. So first of all, just by adding the bispectrum modes, one can better constrain this BO along and across the line of sight and F sigma 8. So this is represented here in orange. They are the constraints of using the power spectrum only. And in green, we have the constraints when the power spectrum is added to the bispectrum. So you see how the green lines are actually smaller than the orange line, which tell us that there is extra information. There is also another reason for using the bispectrum, which is that with the bispectrum, we can break the usual F times sigma 8 degeneracy that we get from 2-point statistics. And this is shown here how this is broken. And the way it's broken is because F sigma 8 is degenerate only at linear scales, but also already going to the nonlinear corrections on the power spectrum, you can break it a little bit. But using the bispectrum is actually the way to go, because the bispectrum is essentially a nonlinear quantity even at leading order. So by including the bispectrum, you are including a lot of nonlinear information where these two parameters are not degenerate, and therefore you can independently measure them. So very briefly, my future research is going towards doing all this type of analysis with DESI. So DESI is a survey, a spectroscopic survey that has already started, and it will last until 2026. It will observe 40,000 square degrees, which represents 1/3 of the full sky. It's spectroscopic, as I have said, and it will cover a redshift range from 0 to 3.5, observing bright galaxies, LRGs, ELGs, quasars, and Lyman alpha. So as I've said, I'm the convener of this RSD and FNL analysis for the year 1 release that we will be out probably by the end of 2022. And I'm also responsible for the developer of the blinding strategy that DESI will follow. So one of the things that we can do within DESI that we have not that I have not mentioned yet is measuring primordial non-Gaussianities. So the primordial non-Gaussianities are predicted by inflation, which is a theory that we require to have the universe flat and homogeneous. But this theory predicts that the primordial field is actually non-Gaussian. So we can parameterize this primordial non-Gaussianity by these parameters FNL and GNL, as I said. And in the early universe, a detection of FNL and GNL would be measuring a bispectrum different than 0. There are constraints on that they are basically telling us that FNL is especially small if it's different than 0. So this has to be at least less than 10. The constraints on GNL are not that high, but in any case. So we barely cannot improve these measurements on FNL and GNL using CMB because all the temperature modes have been observed. We still can use the polarization modes, but actually there is a lot of information on the galaxies. So if we are able to measure the bispectrum and even trispectrum and accurately model the gravitational part, then we can put constraints on the primordial measurement. So from LSS, there are like two ways of measuring this. One is, as I've said, measuring the primordial signal in the bispectrum and trispectrum. Another way to go is to measure a side effect, which is a scale-dependent bias in the power spectrum. So there are like advantages of using these two ways. One of them is to gain more information, because these two phenomena are not going to be exactly are not going to be dependent, they are going to be independent, although they might be correlation. But if we are able to work out the correlation from these two measurements, then we can enhance our signal. Another way of going is that is a way of having a control in terms of systematics, because at least for the power spectrum, the measurement of the scale-dependent bias happens at very, very large scales, and there are a lot of systematics there, and they might be out of control. So in order to make sure that our measurement is consistent, the way to go is to measure this signal in two different statistics. So within this direction, we have performed this paper, which is a first estimate of the trispectrum applied to M-body simulations. We have tested this trispectrum estimate with the Quixote simulations, where in this plot, we are showing the data measurement. So the trispectrum signal extracted directly from this Quixote M-body compared to the prediction of the model. This is for dark matter. But you see that the model and the measurement agree very well, giving you an idea that both are correct. And using the covariance and the modeling, the covariance extracted from the Quixote and the modeling from perturbation theory, then we can quantify the effect of the primordial non-Gaussianities on the bispectrum and on the trispectrum. So in these two plots, I'm showing the primordial contribution of the bispectrum with the gravitational contribution for an FNL equal 1, so like a realistic FNL. And you see that the contribution is very small, is 1 part on 1,000 or even in 10,000. But you have to bear in mind that this is per triangular shape, and we are constraining only one parameter. So when we add all triangular shapes, we are going to enhance the significance of this. This is also shown in the trispectrum signal for the FNL equal 1, but also for a GNL equal to 10,000. And you see here that that you see the effect. So the different orange colors are just showing the effect for real or redshift space. And in these plots here, we are just showing how the error on GNL and error on FNL changes when we include the trispectrum in addition to the bispectrum. And you see that by including the trispectrum in green, it helps on the measurement on the bispectrum alone. So there is extra information in the trispectrum in terms of non-Gaussianities that it can be used. So just to conclude, there is relevant cosmological information in galaxy surveys, especially based on BO and RSD. BOS and EBOS have already measured the expansion and growth across different redshift, and DESI will do better. However, the statistics are limited by the observable volume, and a way to overcome this limitation is to actually measure the bispectrum signal that is still needs to be exploited. So also using bispectrum will allow us to break typical degeneracies like those between F and sigma 8, which are key to test GR effects. And not only that, bispectrum and trispectrum signal are going to be key to measure primordial non-Gaussianities, which are a direct proof of inflation that haven't been detected. So by adding the galaxy in addition to the CMB and to the galaxy higher order statistics, we will be able to constrain primordial non-Gaussianity better than we have now. So using multiple observables make the inference more robust against systematic errors. So this is actually the way to go. And DESI has started to observe it already. And by the end of 2022, year one results will be out, which will supersede the BOS and EBOS result. So I will end my talk here. So thank you for listening. And if you have any questions now, it's the time.